here, so I'm going to do 2 questions. Whoops, let's do them in order. Someone asked me about this as a homework question. At least this is a version of the question that they asked. And it was to try and create a Maclaurin series, because this is centered at 0. The Taylor series that mentioned here is actually for this one. So anyway, we've got this fella, and we're going to try and find its power series, its Maclaurin series. So you start with a function evaluated at 0. You find its first derivative evaluated at 0, second derivative, third derivative, fourth derivative, and finally the 5th derivative. And as I said yesterday, the key to doing this is never calculate anything, just write down the calculation. Now, the first 2 or 3, it's not that clear what the pattern is. I think by the time you get to 4 and 5, you can't kind of see it. Right. Do you notice that there are plus minus going on, which is quite common? You notice that the multiplication on the top is really made up of 2 distinct calculations. There's a 1, 2, 3, and then there's a 2 to the 4. And then there's a 1, 2, 3, 4 times 2 to the power of 5. See that? Now I've got a distinct pattern here. What we can now do is figure out what the nth derivative at 0 would be, because once you've got that, you're pretty much done with the question. When things go plus and minus, isn't it that guy or the n+1 version of that guy? Agreed? N or n+1, what generates this negative plus that we have here?
n+1.
Right. Now, if you want to check it, just pick a number like 5, right? Would you agree 5 plus 1 is 6 and -1 to the 6 gets you a positive? Right. See, if this 5th one had been negative, wouldn't I have used just -1 to the n? -1 to the 5 gets me negative. So just randomly pick one of them. Try out the n. If it matches the sign, you've got it. If it doesn't match the sign, then it's the other guy. Now, there are 2 more things over here. There's this piece, and separate from it, there's this piece. What about the 4th derivative is 1 times 2 times 3. The 5th derivative is 1 times 2 times 3 times 4. So what is the nth derivative going to be?
n-1 factorial.
Great. Now, the second bit is the 4th derivative is 2 to the 4. The 5th derivative is 2 to the 5. So what do you think the nth derivative should be in this story?
2 to the n.
2 to the n. And that package is pretty much the hard part over. So the power series, the sum of everything, Kira, is going to be the nth derivative at 0, x to the n over n factorial, right? In this particular question, do you notice that the value of the function at 0 is 0? Right. What that does is that I start at 1. Didn't we get a question where f of 0 was log 8 or something? And what we did is we stuck a log 8 here and started at 1. So sometimes that first term is best ignored. Oops, is best ignored, right? And then you can look at the formula and see if you need it. Now, the guy that we're going to be looking at is -1 to the n+1, n-1 factorial, 2 to the n, x to the n, all over n factorial.
I have a quick question.
Yes.
So why can't we start at the n equals 0? Because I mean, the log function, the natural log is at least valid at
Yes.
0, and then the normal function seems like the sigma seems to be evaluated at 0. So neither seems to be undefined. So what makes it swift to push?
I got you. It may well be when I'm finished tidying this up, I'll have a look and see if I plug in 0, it works. The advantage of it being 0 is that even if I don't include it, it still works. So I could have two versions of the right answer.
Oh, I guess the -1 factorial wouldn't make much sense. Never mind, everything else makes sense, but the -1 factorial would be weird.
Well, here it would be, but that's going to cancel down in a minute, but it will have a problem connected to that. Would you agree that the n+1 and the n factorial cancel, but what is left with is an n on the bottom? And can you see why I'm starting at 1 there? Right. Now, if that guy at the bottom had been n+1, could happen, right? If that had been n+1, I probably would have put n = 0 in because it would have been fine, it would have worked. Right. Probably. So are we good with that earlier version, which is actually Maclaurin series? There is one last question, and then we move on to applications, which can and will be tricky. Okay, I'm going to call this guy 5, 1 plus x to -1. We're going to evaluate it at 2, so that's going to be a bit interesting. I guess I should rewrite it down again then, because I'm kind of out of sync. If you evaluate this function at 2, you get 5/3. If you find its first derivative, you get -1 times 5, 1 plus x to the -2. And if you evaluate this derivative at 2, and then you tidy it up, you get, eventually you get that. Can you trust me that that's what you get if you make it pretty? Now, if you go second derivative, you get +1 times 2 times a 5, 1 plus x to -3. And the second derivative at 2 ends up being 1 times 2 times 5/3 cubed. And I'm going to do one last one. If you do the fourth derivative, you get a -1 times 2 times 3 times a 5 times a 1 plus x to the -4. And if you, that's the third derivative. And if you find the third derivative at 2, you get a -1 times 2 times 3, a 5/3 to the power of 4. I think I could now get the nth derivative at 2. Right, if I wanted to, couldn't I do the fourth derivative? If I did, it would be +1 times 2 times 3 times 4 times a 5/3 to the power of 5. So, do you see that 1 times 2 times 3 guy, that 1 times 2 guy? Technically, I guess there's a 1 times 5 there. Do you see a factorial? Because that's what I see. So if the third derivative is 3 factorial and the second derivative is 2 factorial, I'm pretty sure that the nth derivative is n factorial. Isn't this another one of those plus minus things going on? So is it -1 to the n or -1 to the n plus 1 this time? Well, I know that's messy, but that says the third derivative. Right, do you see the third derivative is negative? Is that the right version then? Should it be -1 to the n?
Yes.
Yes. Now, there's an awkward 5 that never changes, right? It's 5 all the way through. So I'm putting a little bracket around that just to emphasize it, and I'm sticking the 5 there. And on the bottom, I've got a power. If the third derivative gets me 4 and the second derivative gets me 3, shouldn't the nth derivative get me n plus 1? Are you comfortable with the formula that we've now generated? Now you put that into your n = 0 to infinity, the nth derivative at 2 x minus 2 to the power of n over n factorial. That becomes this fella, this guy, x minus 2 to the n, all over n factorial. We got really lucky, didn't we? A straight cancel. So what I now have is negative 1 to the n 5 times. Oh, I forgot my 3 to the n. I've got my little 3 to the n plus 1. There. Done. So there is the Taylor series for this fractional function centered at 2. So to be able to do these questions, isn't pattern recognition the key? To do 2, 3, 4, some people can see a pattern after 3 derivatives. Some people, you need to go to 5 or even 6 before you suddenly see it. Especially with those series where nothing very obvious happens for the first 2 or 3 derivatives. Yeah, if I stopped, I wouldn't never think of doing this, but if I stopped at the first derivative, would you agree it's quite hard to tell what's happening? Right. Now, if I stopped at that one, do you see there's beginning to be a kind of pattern? And I think by the time I got to this one, would you agree the pattern was becoming even clearer? So it's a workload job. You've got to decide how much work you want to do before you're convinced you see the pattern. And that is, or that will be that. Do we have any questions before we move on to the next section, which is applications?
Could
good?
you could you show how to find the first term that's not a non-zero for f of x series?
I'm trying to think what you're asking again, Alec. I'm not sure. What do you want me to do?
On the homework, we're supposed to enter the first 4 terms, first 4 non-zero terms. I don't know what terms you're asking for.
Okay, so you've got a function. There's one that will have that problem, right? And let's suppose it's Maclaurin's, right? So what you're going to do is you're going to find the first derivative, the second derivative, the third derivative. Who knows how many you do the fourth derivative. And you're going to find the value of that derivative at 0. Put f of 0 down. Now, let's just pretend in this question that that's 0, that this one is 0, and that one is 0, and that this is 2, and this is -4, just for argument's sake, right? Because you can find the derivatives. It'll take forever and a day, but you can find these derivatives and any value of them is 0. What will happen is that it's not uncommon, especially when you have sines and cosines involved, that the derivative at 0 could itself be 0. So the ones that they're asking you to use are the ones where these are numbers. Now, let's take that one. If you are looking at the first derivative being 0, what you get there is, let me just write it down like this. F of 0, f dashed of 0, x over 1 factorial, second derivative 0, x squared 2 factorial, third derivative at 0, x to the 3 factorial, and you could keep going, right, and so on. Now, that's 0. Second derivative is 0, right? And fourth derivative is 0. Do you see in this case only those 2 terms actually exist as values, because 0 times anything gets you 0, right? They disappear. And in this case, you would get 2x over 1 factorial. In this second one, you would get -4x cubed over 3 factorial. You then simplify this down to get 2x, and you try and simplify that, and I believe you get negative 2x cubed. So if the question went and said, write down the first 2 non-zero values, your answer would just be those 2 pieces. Now, if they say, like I think in your example, the first 4, can you imagine you might have to do 8 or 9 derivatives before you got 4 that weren't zeros? And for each one of the ones that wasn't a 0, in this case, these 2, you'd find out what the coefficient at the front was, right? The bits that go here. Get them as numbers, and that would become part of your answer. Does that make sense?
Yeah.
Right.
For the x, if it was a Taylor series, we would just place the x squared, the x cubed with x minus 2.
Yeah. And when you evaluate it, you'd find it at f dash 2, f double dash 2, f treble dash 2, right? Now, in the easiest questions are, none of them are zeros, right? Which means the first 4 answers are the first 4 you're going to use, right? In some cases, you might get, God, that's a horrible one, right? Where every second one is 0. In some cases, you may get the cube one ends up being a 0, but all the others are fine. In which case, you just don't use that one, but you use the one that comes after it. Any other questions?
Yeah, I got one real quick.
Yes, Don.
Question 2 on the homework. The equation is 5x times e to the x. And I don't know if I'm just doing it incorrectly, but I keep getting 0 for my derivatives.
Let me do a couple until you don't get 0, because you will get a 0 a couple of times, right? So I think at least the first time, probably the second as well, right? So make that f, make that g. So the derivative, oh, by the way, f of 0 is 0, right? So we know that the first one is 0. F dash g plus f of g dashed is 5. Oh, this one's going to come out easy. If you evaluate this at 0, you get 5 e to the nothing plus nothing. But e to the 0 is 5, so there you go. So the first one was 0, second one was 5. If you did the second derivative, you differentiate that, and you do a product rule on that, which I happen to know ends up being this guy, which I would combine terms. And then I would do the second derivative at 0, and that would be 10 e to the 0 plus nothing, which gets me 10. So that one would be a 10. So it looks like only the first one ends up being 0, and all the others are nice numbers of some kind.
Gotcha, that helps a lot. Thank you.
You're welcome. Any other questions?
Yeah, for number 14, it's a Taylor series with sine x and a equals pi. And I understand how to get the derivatives in the f of x. I'm just having a difficult time identifying the pattern to get that fn at pi or fn pi.
Well, I have a table in front of me. Thank goodness I happen to have the solutions. If you calculate them, you get the following. The value at 0 is 0. The first derivative at 0 was -1. The second derivative at 0 is 0. And the third derivative at 0 is 1. And then the fourth derivative at 0 ends up being 0. And then the fifth derivative, this one you just keep going. There, I think I see the pattern. Do you see it going plus, minus, and the middle terms are all zeros?
Yes.
Right, so when we are looking for our formula here, what you're going to have to look for is basically the fact that these don't get used, right? And so if you try and generate an nth derivative problem, you can do it, but you have to kind of work on it a little bit harder. So another way of doing this would be just to write down the long version of what the answer would look like, and then try and build a pattern from it.
Okay.
The only time I would do this would be when sines and cosines are involved, because
Got it.
typically this isn't a normal process. Now, if you take out all the ones that don't exist, actually, these should be at pi, shouldn't they? What you get is, I've got it in front of me here, you get a negative 1 over 1 factorial times that guy. And then the next one is plus 1 over 3 factorial of that guy. And then you get a negative 1 over 5 factorial of that guy forever. And what I notice is that that's odd power. So I can do n equals 1 to infinity. And then I have to make this the first term, this the second term, and this the third term. So I'm going to do negative 1 to the n takes care of the plus minus. 1, 3, 5 are odd numbers. So if you do 2n minus 1 factorial, you'll make a 1, 3, and 5 happen. And since these are the same, you can do that. So if you have a sine theta or a cosine theta, you may want to tackle it a slightly different way than trying to generalize the formula, because it's quite hard to make a formula turn into zeros and then ones or minus ones, right? That's not really a doable situation. So it was a kind of write down all the general terms, look at the ones that are left, and try and find a formula that makes this series happen.
Okay, thank you.
If you do the other guy, these are evens. So basically, you just get a 2n and a 2n factorial. So the cosine gets you 1 and the sine gets you another. Yeah. Any more questions? We had a lot of good questions today, so I like that. We go. Right. Word of warning. Part of what is happening in the application questions that we're about to do is discovering what the error would be if you used a Taylor's or a Maclaurin series with values of x in a certain range, right? And when you do those types of questions, there are two methods in which you do it. And one of them involves using a very messy formula, and the other is using your calculator. And I am going to show you the calculator version, because it's much more obvious to do. The WebAssign uses the horrible formula version. Both of them are actually estimates, so it's not like their method actually at the end of the day is better. I mean, the answer they give you is good, but so is the one I'm going to show you. In fact, technically speaking, the way I show you, i.e. doing it with a calculator, is more accurate, in my opinion. So what's that going to mean? It's going to mean, unfortunately, that when you do your homework and they ask you for what is the error, right? What's the worst case scenario? You're going to put 0.006 and WebAssign's going to say it's wrong. And you're going to ignore that. And I'm going to go back and give you the points later, right? There's no way that I can make WebAssign do what I want it to do, but I do want the questions to be done, right? So if you're wondering what the heck's going on, whenever you get the part of the question that says, what's the maximum error? It's called the remainder. It looks like this guy. So it'll say, find that. That's an example of it. Your answer, if you do it my way, ends up being that. And WebAssign half the time, at least, is going to say you're wrong. Because WebAssign thinks the answer is that or something else, right? So you're not wrong, right? You're just doing it in a way that WebAssign doesn't want it. So I've kind of, I've given you the health warning, right, on some of these questions. Now it isn't all the questions, right? But there will be somewhere that happens. So let's look at, I forgot to put our heading. What number are we? What section is this homework? I didn't write it down. It is 1111. There we go. We finally have finished, once this is done, power series, right? Sequences and series. We're finished. So let's take a function. This is an example of question 1. Let's take a function like sine x. And it's going to be centered at 0. So isn't that basically Maclaurin series? And we are going to calculate what are called Taylor polynomials. Instead of calculating an entire power series and putting it in sigma, we've discovered through experience that most of the information is actually in the first 5 or 6 terms of the polynomial. Do you know if you did a power series, but you only use the first 4 or 5 guys, don't you get a pretty good fit? Right? So those polynomials, you know, that you finish with the first 3 terms or the first 5 terms, they're called Taylor's polynomials. So if I asked you, for example, I'm just going to pick this one, to get t of 3, you are going to get f of 0 plus f dashed of 0, that fella, that fella, that fella. Does that make sense? That t3 of x just means only do it up to x cubed. Now, Alec, you've met this in one of your questions. Couldn't there be a lot of zeros in these? And that's okay. Doesn't that just mean that particular term ain't there? And sometimes, couldn't the x cubed be one of those zeros? So a t3 doesn't necessarily have an x cubed in it, because couldn't the x cubed be 0 x cubes? And some people get a little bit distracted when their answer has got 5x squared in it, but it's a t3, and they think, well, should I do the next one? Because, you know, whatever. Should I have 3 terms? No. If it's zeros, it's zeros, right? It is what it is. For that reason, couldn't a t2 of x be the same polynomial as a t3 of x? And that's okay when it happens. In a lot of these questions, they get you to do T1, 2, 3, 4, and 5. So there's going to be some situation like that happening. Now I've got the building block, I guess I should do my working over here. I have a sine function, and its value at 0 is 0. Hey, we've got a 0 straight off the bat. If you do f dashed of 0, it's a cosine of x. And that gets me 1. And if I do the second derivative, I get negative sine x. And the second derivative at 0 is back to being 0. And if I did the third derivative at x, I get negative cosine of x. And that guy gets me negative 1. So do you see that the coefficients I'm going to use, these numbers here, are the ones that go here, 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 and here, right? So far, so good. Right. Let's put the numbers in, see what we get. T3 of x is 0. One of these guys, 0. Negative 1 of these guys. Tidy it up, make it look pretty. 1x over 1 factorial just gets me x. Negative 1x cubed over that guy is negative x cubed over 6. And so T3 of x is that polynomial. I'm going to try and find Desmos for a second. And we are going to look at this guy in Desmos. While I'm doing this, you might as well, you know, put your name down for attendance. I'm almost there. find the right one. Okay, 1, 2, 3. There we go. Darn it, lost it. Wrong one. Okay, what's the difference between a Canadian and a canoe?
What's the difference?
Canoes can tip.
Okay, that was a good one.
I'm sure I've used that one a few times. Okay, I'm clicking on it and it's just, there it is. It's just been darn late. So, okay, so we have got this particular guy and I'm going to put it on Desmos and have a look at it. So first thing I'm going to put in is sin x. Which does what sin x does. And then we're going to put in our next fella, which is what, just x. Take away x cubed divided by 6. Oh, it isn't. X cubed divided by 6. Now, if we look at this guy here, oh, I'm going to restrict the window. And the window I'm going to restrict is from -1 to 1. So here's a little trick I found. You put a curly bracket. You put -1 radians less than or equal to x, less than or equal to x, less than or equal to 1, and you finish the curly brackets. And if I copy this guy, I can put it on the second one. Now what that does is it restricts my picture to just the values of x from 1 to -1. And it looks like they're identical, doesn't it? It looks like I've missed one. So I'm going to zoom in right at the ends. Do you see how close I had to get before I noticed the difference? Now that's only a cube, right? That's only up to the x cubed terms. Isn't that fit? Pretty decent. Now, if I open this range up to say -2 pi and up to 2 pi, and then I do this guy again, and I make sure that both of them are in the same range, and I'll shrink back a little bit. Do you see that there is, the drifting starts around about here, right? And by the time you get to 3, isn't it miles out? So when a Taylor or a Maclaurin, depending on where it's centered, this is centered at 0. So does that mean there's going to be a good fit at 0 and close to 0? But the minute you try and use it for x is 10 or 20, the answer is ridiculous. So how do you think you can make this curve fit better for longer? What's the only thing you have control over?
Keep adding terms.
Yeah. So if I did a T50, I'm not doing it, but if I did a T50, wouldn't you get software to do it anyway, right? You'd get Mathematica or something to do it for you. If I did a T50, could you imagine that'd be a really good fit for a really big chunk of the world? Now, if I said to you, I was going to use this T3 here, and I was going to use it back to my original interval, back to -1 to 1. Wouldn't it be nice for us to have a way of figuring out how good the fit is? In other words, what would the error be? Well, here's a couple of features. Do you notice that the error always happens at the extreme values of x, at the end? Right? And if you go to the end, isn't the worst error going to happen at x equals 1? Or if you travel to the other end, I wish I'd shrank this before I traveled. There we go. or at -1. So if someone then said to you, what is the worst possible scenario if I used this function instead of sine x, right? And I only picked values of x between -1 and 1, wouldn't the error be right at the ends? So wouldn't I only need to find the value of the polynomial at 1 and the sine of 1? And the difference between those two is my error. Does that make sense? So let's do that and see how good is. So I am going to add to this question. So it's not really question 1. Question 1's finished. This is my new question 1. And question 1 says that you're only going to use x's in the range -1 to 1. And you're going to find this guy. He has a name. He's called the remainder function. And the remainder function is described as the value of the function, take away t3 of x. Wouldn't that basically be the error? Right? What the real answer is, right? And what this answer is. So in our case, it would be sine x, take away this guy. Why do you think we put an absolute value around it? What practical purpose would that have?
Because it needs to work for both of the endpoints, and
Yeah,
they
so-
swap which one's on top.
Yeah, we don't really care if the error is plus or minus, don't we? Just care how big it is. So let's try that. So if I wanted to find the maximum value of the remainder function, I only need to find out what is going to happen at the extreme 1. Remember, we're doing interval from -1 to 1. Didn't I show you in the picture? It was at x equals 1 though, is where the drift happened. Right? Now, on our little guy here, the sine of 1, take away, put a bracket around it. What's that? 1, take away 1 cubed divided by 6. Now, I'm about to hit enter here. Do you think that this cubic, this guy here, do you think he is going to be good to 1 decimal place? Or do you think it's even better than being 1 decimal place? Right. So in your mind, say what you think it's going to be, and let's find out what it is.
Isn't that 3
I made a
divided by 6 gonna be a problem?
Oh, I made a mistake. Yes. 1, take away, bracket. 1, take away, 1 divided by 6, close the bracket. Yeah, that's the right answer. Yeah, what is? What's wrong? What heck is wrong? Because I can tell looking at that, that is not a problem. Oh, I know what's wrong. Guess how many people in the world have done degrees when they knew it should be radians? You're in calculus. Keep your calculator on radians. You're never going to see degrees. Right. Back to the question. Sine of 1, take away 1, take away 1 cubed divided by 6. And the answer I get is 0.008. So if I use x take away x cubed over 6 as an approximation to the sine x function, right? I know my answer is going to be good plus or minus 0.008. And that is the worst case scenario. For a lot of the time, aren't I going to get a more accurate answer? Okay. I am now going to do the sine of 0.12345. And I am going to find T3 of X. So that's going to be T3 of 0.12345. So in this case, it's going to be nothing 0.12345, take away nothing 0.12345 cubed over 6. So let's get the estimate first. 0.12345, take away in brackets 0.12345 to the power of 3. And the answer I get is 0.121568634. Just double check that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 cubed, and it's not right because I forgot to divide by 6. So it's 0.123136439. Right, that's it now. This is going to be the correct answer. This is our estimate. Would you be impressed if it was good to 3 decimal places? Would you be amazed at 4? I wonder how good it's going to be. Sine of 0.12345. And the answer is 0.123136. And then it starts drifting. Come on, be impressed. Six decimal places-ish. 6 decimal places. And all I used was a cubic. Aren't Taylor's and Maclaurin series cool things? In the days before calculators, right, you used to have to get a book. Maybe your grandparents used it. I actually am old enough that I used it at school. It was called a 6-figure table. And if you wanted to find the sign of something, you went to the table and it would have, to 6 decimal places, the sign of 1.2, the sign of 1.3, sign of 1.4. And you use those in your calculations. And that's how people calculated sines and cosines. If you ever wondered how did they do it back in the day of 1700s when there wasn't any mechanical electronic calculating machines, they had the books with tables in it, and it was done. A lot of them were done by monks. Monks were just given the calculation, this guy, and they were told to do it for 1.1 and 1.2 and 1.3. And I think, I don't know, but I think they probably got 2 different monks to do it. And if the answers were the same, it get wrote down in the book, right? And if the answers were different, somebody else would do the calculations. I never get disappointed by these. These are just fantastic things. They are so cool. Right, let's go back to a question then. That's kind of what we should be doing. Oh God, no, we're not. There's something else I want to show you instead. Right, here we go. I'll show you what I have in Canvas. It's a little bit more than last time. Put it on student view. Right, are you looking at our Canvas? Right, can I make this a little bit bigger, probably? There we go. There is a module called Midterm Exam Information. If you click on this one, it basically gives you a gist of what's going on. Oh, darn it, in space. So I'll click on that guy. I'll leave student view. I think that's probably half the problem. There we go. Basically, it's telling you when the exam is. It's going to have, I've decided how it's going to work now. There are going to be 10 multiple choice questions and 10 section 2 questions. And the multiple choice questions, you just tell me the answers A, B, or C, and I don't see any working. And section 2, you need to show me work, or you will not get full credit. If I now return back to here, if you click on this one, that's the Zoom meeting. So there's going to be a special Zoom meeting for the midterm, and that's that one you use, not your class one.
Can we just choose whether to show up at the 8 or 9, depending on which one we want to do?
Whatever suits your schedule better, you just turn up. Right. Here, I have a practice one, which for some reason is, it seems to work better if I don't do student view. So what I've got here are just some questions on the types of things that we've been doing. Just scrolling to the end here. Okay, little notation thing. If I get time, I'll fix it. P3 of X is the same thing as T3 of X. Some textbooks call it P3 polynomial 3. Some call them T3 Taylor's 3. It's the same guy, right? So there's an example that's very similar to what we've done today, right? And not only that, but I have the solutions to them as well. Okay, so that's a resource that you can choose to use or not. It's not inclusive. There will be things on the midterm that are not here. Now you have to take your working and get it uploaded for me. So if you click on this link, it gives you a place to get the software for free. Apple guys here, Android here. Here's a cool little video that basically shows you how to use it. When you're finished, you'll have a PDF on your phone of your working. And if you click on this, you can practice uploading your stuff, just so you get used to doing it in case you've not done it before. So this here is just a practice one, right? And looks like I haven't done it perfectly correct. Oh, I probably haven't set up due for the 6th of February. Okay, then I should be able to do that. Is it because I'm not in student mode? Right, let's try student view on it. There we go. Start assignment. If you've got it in OneDrive, click here. If you have it here, choose your file. Oh, pick it. No, pick that one. Say open, submit assignment. And it's as simple as that, right? And you can even, click in some there and see what it's like. Now, if you've had me before, you're probably more used to using this. I've got Microsoft Lens, but there are Cam Scanner. There's another one I can't remember that someone mentioned to me in one of the classes. I think it was their English professor uses it. I don't care what device you use to get it. You can even scan it into your printer if you want, but you have to upload your work. Any questions?
So we don't have to use that specific software in order to upload it. We could just upload a PDF that way, like through Canvas.
Any way you've got it. Have you got a different way of doing it that you're thinking of?
I had my last class a system that I set up for like PDFs and stuff like that, and that one I'm kind of used to, so I just wanted to see if I could use it.
Just keep using it. Some people use old technology, like scanner on your printer. I'm not sure why that's the old technology. It's just as new as any other, but that works too, right? And what you can't do is come to my door and hand it to me as a piece of paper. I don't think that would be a good idea. So it has to be electronic. Any other questions?
Does it have to be a PDF?
It's set up to only accept PDFs. Because if you start giving me weird formats, sometimes I can't open the damn thing. So to make my life easier, it's going to make your life a bit harder, but to make my life easier, it's a PDF because I can open my PDF easily.
Okay, cool.
I think there's lots of software. Isn't there places online, if you don't have it, where you can just drop in a file and it'll PDF it for you, if there is such a word as PDF it, right? It'll convert it to a PDF. So if you do a little search around, you can do it. If you're not comfortable with this, use that practice one that I've got here, right? Upload, it's okay, upload over and 10 times. It doesn't care, it'll rub out the last one. And you can get a good chance of seeing it. I think we're done for today. So bye-bye, have a nice day, and I'll hang about for questions. And we learned some cool stuff today. We learned that a cubic could be a cosine function as long as you keep x pretty small. To 6 decimal places good. That is pretty impressive.
Hey, Professor, could you do number 12 on the 11.10 homework?
11.10, question 12. Sure.
For my question, it's fx equals 8 over x and a equals -2.
Okay, then I don't need to look it up. I'll just do yours. So it's a Taylor series centered at 2.
-2.
Oh, -2, yes. So f of -2 then is 8 over -2, which I am not going to change. I'm just going to leave it as 8 over -2. Now, if I and by the way, if you call this guy that one, it probably makes the differentiation easier. So it's -8x to -2. If I then evaluate the first derivative at -2, God, I get -8 over 2 squared. If I then find the second derivative, I get -8 times 1 times 2, so that's positive, 1 times 2, x to -3. So I'm taking that and I'm multiplying by 2. I'm saying 2 negatives give me a plus. That 8 is just sticking out like a sore thumb. And I'm now beginning to think of a calculation. So technically, couldn't have thought of that as 1 times. So when I get the second derivative at -2, it's going to be a +8 with a 1 times 2 all over -2 cubed. Okay, so got to take care of the sign here. That's interesting. So what am I going to get? 8, 1 times 2 over 2 cubed, and it's going to be negative. Okay, that's a bit messy. There's negatives inside other negatives. Third derivative. It's going to be 8 times a negative, so that's negative. 1 times 2 times 3, x to the -4. Now the third derivative at -2 is going to be -8 times 1 times 2 times 3 all over -2 to the power of 4, which makes this one negative. I think one of my signs up there needs to be changed. No.
On the first derivative, wouldn't the denominator be -2 squared?
Yes, and -2 squared just turns into 2 squared.
Okay, thank you.
So and this one is negative, but that did change the sign. And this one is positive, and that one didn't change the sign. The net effect is, I better put little circles around these guys because it's hard to keep track of the answer, is these are the final things. Do you notice that they're all negative? I was expecting to see a plus minus going, but I guess that isn't happening here, right? So I think I know enough to generate the nth derivative at -2. First thing is, all the answers are negative. All of them contain an 8. The second derivative contains 1 times 2. and the third derivative contains 1 times 2 times 3. Now, if you needed to do the fourth derivative, but can you trust me, it's going to be 1 times 2 times 3 times 4. So that tells me that the third derivative gets me 3 factorial, so the nth derivative should get me n factorial. Are you happy with that? Now, what do you have in the bottom? The second derivative gets me 2 cubed. The third derivative gets me 2 to the power of 4. So what will the nth derivative get me? 2 to the power of?
N plus 1.
N plus 1. We can now put the package together as the nth derivative at -2, x take away 2 to the n over n factorial. So that's -8 n factorial 2 to the n plus 1 and x minus 2 to the n and an n factorial. And we got really lucky here. Cancel, cancel. So it looks like the style point version of the answer
On the top, is it -2 or +2? Does the A be negative switch the sign?
Thank you. It does. Yes. Because it's x take away the number and x take away -2, like you said, is x plus 2. That looks good. I think that is correct, but I know another answer. Where did that guy come from? I mean, this is correct. I'm pretty sure WebAssign will take that. This is just me being pedantic, being fussy. How did this become that?
You turned 8 into 2 cubed or 2.
And then subtracted it from the bottom. Yes.
Yeah.
That's exactly it. In the style point world, would you, oops, there we go. Would you agree that this is slightly prettier, but not amazingly so, right? So I'm pretty sure that's fine, but you know, it's interesting that you could do that. I have any more questions?
Yes, I had one.
Okay, what you got?
So it's still on the number 14 because I was figuring it out and then doing as we went over in class, and I entered the answer in, and then it told me it was incorrect.
So the answer that they have got is n plus 1 x minus pi to the 2n plus 1 over 2n plus 1 factorial. Is that what you have?
No.
Did I do sine instead of cosine, or I did cosine instead of sine?
I think so.
Yeah, that's the mistake.
Put in the minus instead of plus.
Okay.
Okay.
I'll fix it. It is the same process, but but check it. If it says good, we're good to go.
Okay. Yeah, we're good to go.